Hi chemistry students, I'm here to give you another lesson on equation balancing. This lesson is about the SPAM method of equation balancing, and you've probably balanced enough equations now to know that sometimes you run into one that's it's just not obvious how to balance it by the inspection method. It has big coefficients or strange ratios in the coefficients, or lots of, more than 2 or 3 reactants or products, and it's just really complex. The SPAM method will actually work for any chemical equation, but it's really most useful for those that aren't obvious balances by inspection. So it takes a little bit of getting used to, but we find that most students, once they catch on to the method, it really becomes helpful for balancing these more challenging problems. So let's get to it. So now to the SPAM method for equation balancing. Yes. SPAM stands for Smith's Perfect Algebraic Method.
This is actually my chemistry teacher.
And my chemistry teacher.
Okay, yes. We both had the same Smith who taught us the SPAM method for these more difficult algebraic.
I'm not sure whether he invented it, but he anyway.
He gave it a nice acronym for us.
Yeah, so let's get to how to SPAM a chemical equation.
All right, so we're going to start with a skeleton equation. At the top here we have butane combining with oxygen. This is known as a combustion reaction, which we haven't covered yet, and they always form carbon dioxide and water. So that's the first thing to do is write the skeleton.
These can be buggers to balance,
yes,
if you're using that inspection method.
So the first thing we want to do is give these all some kind of letter to represent them. I'm going to choose X, Y, Z, and W for each one. So, X, Y. So instead of numbers, we're just going to give them letters. Like we're going to treat them like math. So then our next step is to write out an algebraic equation for each thing on the left side compared to its counterpart on the right.
So we only have 3 elements here,
we have carbon, oxygen, and hydrogen.
Oxygen.
So basically we're going to start with carbon and say, all right, I have 4 carbons, so that would be 4x equals,
and we look on the right side.
On the right side, and there's only 1 carbon on the right, so it equals 1z, or just z in this case.
So that's the first equation, 4x equals z.
Then we want to take the next one, so let's say hydrogen. So on the left side, or the reactant side, we have 10x equal to 2w, because H2O has 2 hydrogens, so it's 2w. Your 2 and z's look similar, but I understand what you're doing there.
That's what the little cross-hatch is.
Right, and then lastly, we have oxygen. Nice. Last, we have oxygen, which we know 2y, since the other side has just O2, so it's 2y, equals, I have you paranoid now, equals 2z, because CO2 has 2 of them, so it equals 2z plus w. Because
there's
water
only 1 oxygen in the water. Okay, 2z plus w. So what we've got is a system of equations, much like you do in algebra, except we have 3 equations, but 4 variables in this case. And this is a tricky one, but the next step kind of helps us make all this complexity become fairly simple. We can arbitrarily set the value of one of these variables as a 1.
Yeah, in this case, let's choose x.
So you usually would choose something that you think probably would have the lowest coefficient, or might be a 1, which is probably going to be the thing that has the most atoms in it.
So in this case, it's going to be x.
So we're going to pick that butane, and we're going to set x equal to 1. So we're going to arbitrarily say x is 1 in this system, and then we just go back, well, if x is 1,
so that means 4 equals z.
That 4 equals z, so z is 4. Then we bring the solution for z.
We have other x's we can change too. We also know that now 2w equals x.
So 2w equals 10.
Yes,
right?
all right.
2w equals 10, so w solves out to be 5.
Yep.
Okay. And now we can come down into there's usually one, this one's got 3 variables in it here, so we kind of have to do that one last.
Yep.
But now we know what the values of everything except y is. Okay, so we can go back,
2y.
substitute in here, 2y equals 2 times z. Well, z is 4, so that's 8. 2 times 4 is 8.
Plus w, which
Plus
is
w
5.
is 5.
So 8 plus 5
is 13.
So 2y equals 13.
So y equals
6.5.
13 halves.
Or 6.5.
Or 6.5. Or
So
6.5.
since
now,
we can't have half a mole, we have to take all our values and multiply them through by 2.
Let's write out the whole equation.
All right, let's do that first.
With everything, and then we'll kind of go through. So we're going to go back up here. We're going to say x is 1, so it's going to be C4H10 plus y we said was 13 halves. 13 halves O2 yields Z is 4 CO2 plus W is 5 H2O.
I forgot how fun the spam method was.
Okay, so and honestly, to work that out with the substitution method, you could do it, and you'll get the same thing. It's a lot of trial and error. But now go back to your original point there, Mr. Hunter.
Now, since we can't have half a mole in our chemical equations, we have to multiply it all to make it whole. So we'd have to multiply them all by 2.
So that becomes, oh, you dummy. There we go. That becomes 2.
That one becomes 13.
13, so we'll just get rid of the 2 down there.
The other one becomes 8.
So this becomes 8.
And the last one becomes 10. And then you have a balanced chemical equation. And you can do this to any chemical equation, but we would suggest only the ones that would require the use of difficult problem solving instead of the easy ones.
Yeah, ones that have multiple reactants and products and
Right,
aren't easily solvable.
Let's take a look at that one we stopped with last time.
So we're going to try the spam approach on another equation, and you might recognize this one. This is the one we ended the first video on balancing with, and this is one that was not an easy one to balance by simple inspection, but the spam method will help us on this one. So we're going to, again, random variables for the coefficients. So I'm going to put x. I'm going to write them up a little higher so I can put the actual numbers in below when I get them worked out. And then for carbon monoxide, we'll give it the coefficient y. For iron, we'll give it the coefficient z. And for the carbon dioxide, we'll give it the coefficient w. You can use any letters you want. That's the letters that I chose. So we're going to write an equation, an algebraic equation, for each element in the formula. So we're going to write one for iron, one for oxygen, and one for carbon. So if we look at the left side, iron appears in the first reactant, Fe2O3, and it's going to be 2x. So 2 because the subscript is 2, and x because the code, so it's 2 times x. And we're going to set that equal to Z, because the iron on the other side is here. It has no subscript, just the coefficient Z. So the iron atom is going to be 2x on the left equals Z on the right. Okay, now let's write an equation for oxygen. So now we have to remember, oxygen shows up in both reactants, but only one product. So we're going to start with 3x plus y, because there's 1 times y in front of the carbon monoxide, equals 2w. So there's an equation with 3 different variables in it. Then we'll go on to carbon. Carbon shows up just here and just here. So the equation for carbon is very simple. It's y XY equals W. So that's a Y. So now we're going to arbitrarily choose one of the letters that we want to be a 1. And I'm going to pick X. So I'm going to make my X a 1. So we'll come over here and kind of write the solutions. If X is 1, that means that Z, if we look at the first equation there, must equal 2. So if you stick in 1 as the value of X, then Z ends up being 2. So if we come down here to this equation, then we can substitute in 1 for X there as well. And then because there's 3 variables in the equation, and even if we put a 1 in for the X, we still have 2 variables, Y and W. We need to come down to the third equation and look and say, well, Y and W are the same thing. So I can actually pick one of them to replace. So I'm going to rewrite this entire equation. We're just going to say 3 times 1, which is X, is just 3, plus, and watch this, I'm going to change this to W, because Y equals W according to this equation. So instead of Y, I can just replace it with W equals 2W. And then 3 equals W, which also equals Y because they're the same thing. So 3 equals W equals Y. Okay, so now we can go back through and substitute in the rest of the numbers. So 3 and Z is 2 and W is 3. So that's our final equation. 1 Fe2O3 plus 3CO reacts to produce 2 Fe and 3 CO2. SPAM method strikes again, gives us a successful solution. Okay, so let's combine a little demonstration with some equation balancing. Here's a demonstration that we showed you in class the other day, if you were there, decomposition of ammonium dichromate. So let's watch. Okay, so we got to see the ammonium dichromate decomposing. Now let's take a look at the chemistry there. So you're going to want to copy this equation down. We have ammonium dichromates, the Cr2O7, and it's breaking into Cr2O3, N2, which is nitrogen gas, and water. And I've put in, instead of X, Y, Z, W, I put in A, B, C, and D as our variables for the balance. So now let's write equations to go with each one of those. So for our nitrogen equation, we're going to write 2A because there's a 2 outside that ammonium, so it's 2 times the N multiplied by the A equals 2C. So in other words, A equals C. Alright, for hydrogen, what we have for hydrogen is going to be 8A, 2 times 4 times A, equals 2D. Which means then, if we divide out 2, 4A equals D. Are you with me? Alright, now chromium is part of that first reactant there in the decomposition. So that's going to be 2A equals 2B, which reduces to A equals B. So now we also know that A equals C, so that means A, B, and C are all equal. Okay, which brings us to oxygen. So for oxygen, we have 7A, 7 times A equals 3B plus D. So now let's pick something to set as a 1. And boy, wouldn't it be nice if we could just, since we have 3 variables that are equal, A and C and B are all equal. So let's take a risk here. We're going to set all of them as a 1. Now, if it's wrong, we can always fix that when we're done, but that just makes them basically the only thing we need to worry about is D. Okay? So if we just look at this equation then here, then 4 times 1 equals D, so D is 4. And boy, that worked out beautifully, didn't it? So in this case, and again, it's actually a pretty simple solution. All of them have coefficients of 1 except for the water, but looking at that looked like it was going to be incredibly complex. So it does take a little time to set up the equations, but then just arbitrarily pick something to be the 1, and a lot of times it'll just work itself out really quickly, the system of equations, and you've got your coefficients. So we will practice this some more in class with both the inspection method and the SPAM approach. Until then, have a good evening. Okay, so for our post-video question, we've given you a combustion equation. We have a hydrocarbon here, C5H12. That would be pentane, combusting with oxygen to give us carbon dioxide and water, and we're going to try to SPAM balance this. So let's first of all assign variables to all of these. So we're going to say that the first coefficient is A, the oxygen coefficient is B, we'll make that C, carbon dioxide, and D, H2O. So the first thing we need to do, remember, after assigning the variables then, is to write an equation for each element. So we have carbon, hydrogen, and oxygen. Okay, let's write the carbon equation. 5A, because the coefficient is A, and there's 5 carbons in C5H12. That's the only carbon on the left, equals C, because there's 1 C in CO2. Alright, now what I would like you to do is you write the equation for the hydrogen and for the oxygen, and then attempt to solve it and see if you can figure out what number should actually go in for A, B, C, and D. Remember, after you write the equations, you arbitrarily pick one of the variables that you're going to set equal to 1. If I was you, I would probably set A equal to 1, but it will actually work out to the same answer no matter which one after you solve it and then get rid of any fractions that you have. So good luck, and we'll discuss this more the next time.